All right, how about now? Can you guys hear me? Okay, good. Sorry about that. I think the microphone was on a default, different default. So just for people on Zoom, I just mentioned it here that the midterm two date for that is going to be Tuesday, April 21st. That is one lecture later than what is planned in the syllabus, and so if you're going by the syllabus, the midterm's not going to be next Thursday. So that's when it was originally planned. I pushed it back to next Tuesday just so that we have time to get homework 6 in there for you guys to practice for midterm 2. Okay. Okay, and so besides that, I think that's about it. Are there any questions about anything before we get started for today? Okay, all right, so let's go ahead and get started. So topic for today, we kind of finished everything with regard to the Fourier series before we left for spring break. So that's everything that you need for homework 5. Today we're starting kind of an add-on to that called the Fourier integral, and then by extension the Fourier transform. Okay. Okay. So today will be kind of a lot of the motivation, a lot of the conceptual information, and then we'll do more examples and more problems on Thursday. Okay. Okay. So let's start with this. So before we left for spring break, we finished covering what I call the discrete Fourier series. Okay. With emphasis on the word discrete. And I'll kind of explain what that means in a second. Right. So just to kind of jog your memory, right? Remember, the Fourier series was a method for functional representation. So you can take any periodic function f of t. Right? And remember, the requirement is that the function has to be periodic, so it does have to repeat itself on a fixed interval, right? We can represent that periodic function using an infinite summation of sines and cosines, right? So we said f of t is equal to a0 plus infinite summation, so summation from n is equal to 1 to infinity of an cosine n pi t divided by L plus bn sine of n pi t divided by L. Okay. Right. Where L, of course, L is the period of our periodic function. Right. And then these coefficients, A0, AN, BN, right? We call these the Fourier series coefficients. And a lot of times when you're doing your Fourier series problems, a lot of times we're interested in the values of those coefficients. Right. So if you haven't had a chance to start homework 5 yet, you'll get a lot of practice, a lot of familiarity with computing those coefficients. Okay. Okay. So I call this the discrete Fourier series because, if you look at the frequency component of our sines and cosines, only a certain amount of frequencies are represented, right? And so if we kind of look at this, right? So the frequency component of our sines and cosines are kind of what I highlight here. So that n pi over L, right? Right. So remember, n is not just any number. Remember, n is the index of our summation. So n has to be a whole number. Okay. And so n is limited to a whole number. Now, granted, n does eventually go up to infinity, right? That does limit how many frequencies that we can do, right? So we can only look at frequencies pi over L, 2 pi over L, 3 pi over L, 4 pi over L, so on and so forth, right? right? We can't look at, maybe 1/2 pi over L or 2.5 pi over L or, 6.7 pi over L, right? So, we're only looking at integer multiples of that. You can call that pi over L, you can call that maybe the fundamental frequency of our expansion. Okay. All right. So in a lot of situations, that's fine, right? There's no harm in computing just these discrete frequencies. But there's also a lot of applications where we may actually be interested and maybe some of the frequencies that are in between these integer multiples. Okay. Right. So let's say we're interested, what would be the Fourier series coefficient of 1.5 pi over L of that frequency, right? What if we wanted to know what the coefficient for 2.3 pi over L is, right? Right now we can't do that with the Fourier series, at least as it's currently constructed, unless we look at a function with a greater period, right? But the limiting factor here, of course, is the period, right? Right. So the longer the period, then there's a broader range of frequencies that we can look at just because the period there isn't enough. Okay. So the Fourier transform kind of aims to rectify kind of both of these issues, right? On the one hand, it'll allow us to look at a broader range of frequencies, not just discrete frequencies, but a continuous spectrum of frequencies. But it will also let us apply this Fourier methodology to non-periodic functions. Okay. Right? And a non-periodic function is one that does not repeat, right? It's non-periodic. And so you can make the argument that a non-periodic function will have a period of infinity. Okay. So that's kind of the motivation. So the motivation for this unit here is to basically kind of take what we understand from the Fourier series, what we understand about frequency, and then let's try to apply that to our non-periodic functions. Okay. Okay. All right. Any questions on this so far? Okay. All right. So to begin, we have to kind of talk about something called the Fourier integral. Okay, so let's go there. Okay, so you can think of the Fourier integral as kind of an extension or generalization of our Fourier series, where basically, we're going to take the summation of our Fourier series, and then we want to turn this into an integral instead. Okay. Okay. So let's start with this. So let's look at our Fourier series one more time, and let's write out the equations for our Fourier series coefficients. Okay. Remember, so we had three of them. So we had A naught. A naught was simply just our mean value formula. So A naught is 1 over 2L integral from minus L to L f of t dt. Okay. Then we have AN. AN is 1 over L integral from minus L to L f of t cosine of omega n t dt. Okay. Now I did make a substitution here. So, if you notice here, I didn't plug in the typical value here, where omega n here, omega n is the same thing as n pi over L. Okay. Right. So I just shortened it to omega n just because we're going to be, writing it along. Okay. All right. And then finally we have Bn. Bn is a very similar formula to An, but it has sine instead. So Bn is going to be 1 over L integral from minus L to L f of t sine omega n times t dt. Okay. So the week before the spring break, we were essentially working with these formulas here to determine our Fourier series coefficients. Okay. And then eventually what we did was once we evaluated these integrals, we took those expressions and plugged it back into our series and computed the first, 3, 4, 5 terms, right? So let's do that here. So let's take these expressions and plug them into our Fourier series expansion. Okay, so this is going to be a little bit long, so just kind of bear with me as we're plugging into an expansion that's already long, and then our expressions for the coefficients are also long as well. Okay, all right. So remember, our Fourier series expansion f of t is equal to, first thing we have is a naught, so let me go ahead and plug in for that. So that's going to be 1 divided by 2L integral from minus L to L f of t dt, okay, plus, since both AN and BN have this 1 over L, I'm going to factor it out of the summation. So we're going to have a plus 1 over L summation from n is equal to 1 to infinity. We have cosine omega n times t times integral from minus L to L f of t cosine of omega n t dt. Okay. So that combination of terms right there, that is AN multiplied by cosine omega n t, right? So I just plugged in for AN. I kind of swapped the order just so you don't get kind of confused with the which cosine is inside the integral and which one's not. Okay. Plus sine omega n t integral from minus L to L f of t sine omega n t dt. Okay. Okay, so that's basically our Fourier series expansion. So we haven't done anything special yet. So we've just taken our Fourier series expansion and we just plugged in for the coefficients, right? So if you're really short on space, you can kind of just write this one line here. But I think typically we have the coefficient equation separate just because it makes it easier to. Okay. All right, so now that we have it in this form, remember we're aiming to eventually apply this to non-periodic functions. And so the way we do that is we need to take the limit as L approaches infinity. Okay. But if we do that from here, we're just going to end up with 0 everywhere because we have L in the denominator for both the initial term and for the summation. So let's make a substitution here before we do that. Okay. Okay. So to do that, we are going to have to kind of pull something a little bit out of our, a little bit out of our bag of tricks here. So we're going to define a new variable, right? So the new variable that we're going to define is delta omega here, right? Which represents a change in omega. Okay. So this delta omega here is going to represent the change in mode from one to the next. Okay. So essentially, when you're essentially increasing the value of n, right? So when you go from n is equal to 1 to n is equal to 2, this delta here represents the change in frequency that occurs. Okay. Okay. So in other words, this is basically n plus 1 times pi over L minus n pi over L, right? Where n pi over L, that's maybe the current frequency that we're looking at in our Fourier series, and then n plus 1 times pi over L, that's the next frequency. So delta omega is just going to be the difference in between those two. Okay. Okay. So of course we can do this subtraction. So this subtraction is very straightforward. So the n pi over L is going to cancel out. And so all we're left with is just pi over L. And then we can use this to make a substitution for L, right? Because if we kind of just equate the beginning of this equal sign to the end, we have delta omega is equal to pi over L, right? We can then bring the pi to the bottom, and we can say that 1 over L is equal to delta omega divided by pi, okay? So we've basically introduced this new variable, this delta omega, and we're going to use it to make a substitution for 1 over L, okay? Because now we can take this and plug it in for this guy up here. Okay. Okay. All right. So let's go ahead and make that substitution. It's going to make our expression a little bit longer, but we can go ahead and do that. All right. So we go ahead and plug in for that. We end up with the following. Right. So this first term right here, we're actually going to keep it as 1 over L. We know it's going to cancel out. So once we take the limit as L goes to infinity, that first term is going to cancel. But for a non-periodic function, the concept of an average is not as clearly defined. So we're fine with that term canceling out. Okay. So the first term we're going to leave alone. We're going to have 1 over 2L integral from minus L to L f of t dt plus 1 over pi. So I'm basically taking this delta omega over pi. I'm factoring out the 1 over omega, and we're going to distribute the delta omega throughout the summation. All right, we have summation from 1 to infinity, cosine omega n times t times delta omega, integral from minus L to L of f of t cosine omega n t dt plus sine omega n t delta omega integral from minus L to L f of t sine omega n t dt. All right. We get a little bit of a monstrosity here, but this is as bad as it gets. So now we are going to take the limit, and that is going to simplify things a bit for us. Okay. Okay. So now that we have our Fourier series in this form, we can now take our limit. Okay, so we're going to take the limit as L approaches infinity. Okay. So remember, when you're dealing with infinity, you can't just plug infinity into these equations. You have to take the limit. I mean, effectively, we are plugging in infinity, but just mathematically, we have to take the limit. And what this is going to do is that this will allow us to apply our Fourier series to a non-periodic function. I underestimated my space there. Okay. Okay, so by taking this limit, there are three things that are going to happen. Right. So number one, right. So first obvious thing that happens is that we still have that 1/2L term in front. We take the limit as L goes to infinity. We have 1 divided by 2 times infinity, which is essentially 0. Right. So first thing that's going to happen is the first term will go away. Okay. Right, and that makes perfect sense because when you have a non-periodic function, the idea or the concept of an average doesn't really quite exist anymore. Right? And so it's like asking you to take the average of f of x is equal to x squared, right? X squared technically goes on to infinity. And so if you're taking the average of that function as it goes to infinity, then there's really no kind of concept for it. Technically the average is infinity, right? And so it doesn't make sense that if we're looking at non-periodic functions, it doesn't make sense for us to compute any average. Okay. Okay. Number two. Second thing that's going to happen is that our delta omega here will get infinitesimally small. Right? Right? So in other words, the difference in frequencies between successive modes in our series is going to get so small that it's essentially going to be a continuous function. Right? Okay. So we kind of solved our initial issue. Where remember, one of the initial issues we had with the Fourier series that we can only look at discrete frequencies. But now that we're looking at a situation where L goes to infinity, we're not looking at discrete frequencies. Well, technically we still are. But the differences in between those frequencies is so small since L goes to infinity, right? So mathematically, the way that we represent this, right? Instead of delta omega, where traditionally in a math context, the delta there represents a discrete difference, right? But now, when that discrete difference is infinitesimally small, we represent that with a kind of almost like a derivative expression. Right? So d omega as opposed to delta. Okay. And then the third and final thing that happens, it's kind of a consequence of point number 2, is that our summation now is going to change. Okay. Because before, our Fourier series was a summation of discrete frequencies with discrete coefficients, right? Okay. So our summation over discrete frequencies will instead become an integral over a continuous range of frequencies. Right? Right. And then because of this also, because of the fact that our L is going to infinity, not only are we doing an infinite, not only doing an integral, but it's an integral with infinity bounds, right? So in other words, mathematically, we're doing this. And so we're changing from this over to integral from minus infinity to infinity, right? So remember our original summation there, our original integrals were from minus L to L, but since now we're taking the limit as L goes to infinity, we're now taking infinite integrals. Okay. Okay. So all that said, so that's kind of a lot of words for for a much simpler result than I think than what this makes it seem. Okay. And so we do all that, we end up with the following. So we get f of t is equal to 1 over pi. Remember, our first term no longer exists, right? Summation from 0 to infinity. Okay. I'm sorry, one small mistake here. So for our summation here, it's not integral from minus infinity to infinity. It's integral from 0 to infinity. I apologize. One small typo there. Yeah, we do have an integral from minus infinity to infinity, but that's for the coefficients. Okay. All right, so our f of t here is 1 over pi, integral from 0 to infinity, cosine omega t, another integral from minus infinity to infinity, f of t, cosine omega t dt, plus sine omega t, integral from minus infinity to infinity, f of t, sine omega t dt. All right, so this expression right here, this is what we call our Fourier integral. You can think of it as kind of the continuous form of our Fourier series. Okay. Right, but there is a slightly more convenient form. So this is the full form right here. But typically we use another form just to kind of make things a little bit more convenient for us to compute. We use another form because the other form is more kind of analogous to our Fourier series as well. Okay. So oftentimes we break this up into two different frequency functions instead. Okay. So what we say is that this expression right here, right, and this expression right here, right, If you kind of trace this back to the beginning of the derivation, those expressions there came from our Fourier series coefficients. So that was an, the first highlighted term is an, the second highlighted term is en. Okay, so we can actually compute kind of analogous representations of that, right? We can say that our a of omega, right, is equal to 1 over pi integral from minus infinity to infinity f of t cosine omega t dt, okay? And then b of omega is equal to 1 over pi integral from minus infinity to infinity f of t sine omega t dt. Okay. So I'm going to box these ones just because these ones are the ones that are a bit more useful. Okay. Right. So this right here is kind of our first look. It's not the final form, but it's our first kind of look at what we kind of consider the Fourier transform. Okay. There's going to be various forms of the Fourier transform. This is not, we'll go over other forms, and actually other forms are actually a little bit more convenient. But we'll call this the sine and cosine versions of our, of our Fourier, Fourier. Okay, so that was a lot of talking on my end. Sorry, it was a long derivation. Any questions on this so far before we do an example? Okay, all right. So let's do an example really quickly just to kind of see what this would look like. Okay, so basically with these expressions right here, we can use them in basically the same way that we use our Fourier series. So we can take the function in the time domain and then basically take its Fourier transform. Okay, so let's see how that would work. Okay, so for this example here, we are going to find the Fourier integral representation of a square pulse. All right, so our square pulse is going to look like the following. So between -1 and 1, our function is going to have a value of 1. Okay. But it's going to be 0 at all other values here. So this is prime candidate. So this is a function here that's not periodic. And so we know right away that this pulse is not going to repeat. It's just going to pulse once and that's it. Okay. So functionally or mathematically, we can say that f of t is equal to 0 when t is less than -1. It's going to be equal to 1 when t is between -1 and 1. Okay. And we can say that t has a value of 0 at all values t greater than 1. Okay. Okay, so we want to find the Fourier integral representation. So essentially what that means is that we need to first compute a of omega and b of omega. Okay. And then once we compute a of omega, b of omega, we're going to plug that into the integral representation. Okay, so just exactly like we did with the Fourier series, except now instead of discrete coefficients, and now we have a continuous function of omega. Remember, omega here represents frequency. Okay. And you can kind of you can kind of make the same assumptions that we did for Fourier series as well. So you can tell, from this function here, even though it's not periodic, right, you can tell that it looks like an even function, right? So it looks like a function that's going to be symmetric across the vertical axis. And so by that logic, B of omega should be 0, since it kind of has that even characteristic. But we'll see and kind of confirm that after we compute it. Okay, so first let's compute A of omega. So A of omega, let's go ahead and plug into the formula for that. So we have 1 over pi integral minus infinity to infinity of f of t cosine omega t dt. Okay. All right. So let's go and plug in this function. And so, just like a lot of times when you see in Fourier, we have a discontinuous function. So we need to break this up into our 3 regions. So we're going to have an integral from minus infinity to minus 1 for the function 0, right? So we're going to have 1 over pi multiplied by integral from minus infinity to minus 1, right? The value of the function at that time is 0. Okay. Plus integral from minus 1 to 1, right? The value of the function between minus 1 to 1 is 1. Okay. Cosine omega t dt, plus another region from 1 to infinity where the value of the function is 0. So we have integral from 1 to infinity, 0 times cosine omega t dt. And I forgot to close bracket. Close bracket. All right, so obviously the first and the third integral are going to be 0 just because we have integral of 0, which is 0, right? And so these ones are going to cancel out, right? And so all we're left with there is just integral from minus 1 to 1 of cosine omega t dt with a 1 over pi out in front. This is equal to 1 over pi integral minus 1 to 1 cosine omega t dt. Okay. So let's go ahead and perform that integral. So that integral there is going to be 1 over omega times pi sine of omega t. And we're going to evaluate this from minus 1 to 1. All right, so this is a pretty simple evaluation here. So we have, we're going to plug in for t. So you have 1 over omega times pi sine of omega minus sine of minus omega, right? You notice here that our function here does not have t anymore. And that's typical, right? So essentially we're performing a transform. So we're taking the t and we're integrating it out and we're replacing it with omega in a sense. Okay. All right, let's use the fact that sine is an odd function. So sine of omega minus omega is equal to minus sine of omega, right? So basically that negative comes out in front because sine is an odd function. And so we have sine of omega minus negative sine of omega. The two minuses are going to cancel out. And so our result from this is A of omega is equal to 2 sine of omega divided by omega times pi. All right, any questions on how we got that result there? Okay, good. All right, so that's one, it's not really a coefficient, but that's one expression for our Fourier transform that we have in the back, right? Now let's compute the other one. So our other one is B of omega. So B of omega is equal to 1 over pi integral from minus infinity to infinity of f of t sine of omega t dt. Okay. Right, so that's just the formula for b of omega. That's the sine part of the Fourier transform. Okay. So we still have the same function here. So our function here is still, going to be 0, everything outside of -1 to 1. Right, so I'm just going to skip that step. And so I'm just going to say this is going to be equal to 1 over pi integral from -1 to 1 sine of omega t dt. Okay, so I basically did the same thing as up here where I kind of split the integral into 3, but I knew that the first integral and the third integral are automatically going to be 0 because the function is 0 during that time. And so we just end up with an integral from -1 to 1. Okay, so let's go ahead and perform this integral very quickly. And so integral of sine omega t there is minus cosine omega t. So you have minus 1 over omega pi cosine of omega t, evaluated from -1 to 1. Okay. All right, so let's go ahead and plug in our integration bounds for t. So that's a -1 over omega pi. We have cosine omega t minus cosine of, not cosine omega t, cosine of just omega. So cosine of omega minus cosine of minus omega. Exactly, right? Yeah, because remember, cosine is an even function. So since cosine is an even function, cosine of minus omega is equal to cosine of omega, right? So that basically just cancels out the negative. And so inside that parentheses there, we have cosine omega minus cosine omega, which is just 0, right? So b of omega is just 0 in this case, right? Which tracks with kind of what we assumed initially for the function. Because our function here, f of t, right, it was symmetric across the vertical axis. And so we kind of expect this to be an even function. And so the same kind of logic applies here. So b of omega there is okay. Okay. So now that we have our expressions for a of omega, b of omega, we can plug them into our Fourier integral, right? So remember, the important thing is, don't stop here. So it's just like the Fourier series. So the problem is not complete just by computing the coefficients. You do have to go back and plug it into the series, or to the integral in this case. Okay. Right, so let's take these and plug these into the Fourier integral. Okay. So we have f of t is equal to, I don't think I had this expression explicitly up there, but I'm going to go ahead and write it here. All right, so f of t is equal to integral from 0 to infinity, a of omega cosine of omega t plus b of omega sine omega t d omega. Okay. So this is actually the same integral expression that I had above. It's just I plugged in for a of omega to d omega. This one is the little bit more convenient form. Okay. All right, so we go ahead and plug in for our expressions here. So b of omega is equal to 0. So that second term there is just going to cancel out. And then we plug in for a of omega that we obtained earlier in the problem. Okay. So we get f of t is equal to integral from 0 to infinity. A of omega here is 2 sine of omega divided by omega times pi times cosine of omega t d omega. Okay, so that's kind of the basics of a Fourier transform problem. So it kind of proceeds very similarly to our Fourier series problems, where I'm going to give you a function in the time domain, and then you basically have to apply the formulas for the coefficients, or in this case, the Fourier transform, get expressions for a of omega, b of omega, plug it back into the Fourier integral. All right, any questions on this example here? Okay, good. Okay, so next thing we're going to talk about is a little bit about the properties of this Fourier integral itself, right? And actually one very specific property that we're going to look at, which is what happens when you come up to discontinuities, which leads to something called the Gibbs phenomenon. Okay, so when we're doing Fourier, so this applies to both Fourier series and the Fourier transform. We're just naturally going to be looking at functions that have a lot of discontinuities. Okay? So a discontinuity is basically whenever a function kind of rapidly jumps from one value to the next. Okay? So the past example that we just did, it actually technically had two discontinuities, right? And so if we draw out the function from before, right? Right. So our function from before looked like the following. So we had a function that looks like this, right? So technically when t is equal to -1 and t is equal to 1, we have a discontinuity, right? Because the function just changes from 0 to 1 and then from 1 down to 0. Okay? So discontinuities are very interesting mathematically because technically, if you look at it, right? And so if you ask the question, what is the value of f, or what is the value of a function at t is equal to -1? Well, technically, it has two different values, right? So it has a value at the top of the discontinuity and a value at the bottom of the discontinuity. Which I can't take. Function has two values. Right? Because when you have kind of a discontinuity, right, it jumps from one value to the next, that jump has to occur at some point. And so wherever that jump occurs, your function technically has two values, which is illegal, actually. So instead of having two values, technically we say that the function is undefined at that location. Right. And that can cause some issues as you can imagine. Right? So let's say you're trying to do some quantitative analysis on a function like this. Discontinuities are not, they do happen, right? So if you're talking about in the realm of like signal processing, there will be times when the signal kind of maybe suddenly jumps or maybe suddenly cuts out. And so when you're processing raw data from like a sensor or something like that, discontinuities they're just a reality of things that happen, right? So when we do analysis or when we do, kind of interpretation or processing of these kinds of data, we need a way to kind of mathematically handle these types of situations. Okay. And it turns out Fourier actually gives us the great tools for that type of analysis. Okay. So when you represent a function like this with Fourier, okay. So whether that be Fourier series or Fourier transform, they both kind of have the same effect, right? They kind of have this effect where they kind of smooth out the discontinuity, right? And so it actually it actually clearly defines a function value at every location. Okay. And so instead of having two simultaneous values or an undefined value at a discontinuity, the Fourier series or the Fourier transform does have a value there, right? And the value there actually is exactly what you intuitively think it to be. And so when you represent a function with Fourier, right, the discontinuity value ends up just being the average of the two ends of the discontinuity. Okay? So for example, right? So for this function, right? So this function here, we have discontinuities at t is equal to -1 and t is equal to 1, right? So the function jumps from 0 to 1 and then 1, right? So the average between those two is just 0 plus 1 divided by 2 is 1/2. And so if we were to represent this function with Fourier, right, it doesn't matter, Fourier series, Fourier transform, doesn't matter where you truncate it at, how many frequencies you put in, you always get the same result, right? Right, so we say f of -1 is equal to 1/2. And f of 1 is equal to 1/2 as well. Okay. Whereas previously, for that square pulse, technically f of -1, f of 1 were undefined previously. All right, so that is a nice feature because there are situations. So kind of like we talked about last time, right? So whenever you're taking kind of raw measurements of stuff in the wild, you're always going to have noisy data. You're going to have data that kind of cuts off. You're going to have data that kind of goes up and goes down, right? Having a way to kind of deal with these discontinuities and still allow you to do any kind of analysis or any kind of calculations is incredibly valuable. So this is one of I would say one of the main engineering benefits of Fourier, where it lets you essentially smooth out these functions and let you evaluate things which previously may not have a clearly defined value. Okay. All right. Any questions on this? Okay. But then that kind of leads to the next point. Right? So how does it do this, right? And so, it's this all sounds well and good, but how exactly does it actually, produce a value here? Right. So what is it about Fourier that has these kind of smoothing properties? So what is it about it that has it go over these discontinuities? Right. So the thing to remember with Fourier is that Fourier at its heart is just basically taking your function and representing it using sines and cosines. So Fourier series, Fourier transforms is saying that you can take any function and just represent them by just summing up a bunch of sines and cosines. And just by their nature, right? So because sine and cosine, those are continuous functions, right? When you add up a bunch of sines and cosines together, you add up a bunch of continuous functions, you end up with a continuous function. So that's kind of how it works. But actually something very interesting happens because we're using sine and cosines, right? So let me kind of draw out our square pulse again. I know we've kind of abused this example today, but it's very useful. So there's our square pulse. I know, I tried to improve it as the lecture went on, but the square pulse is still lopsided. So it looks like the right side's bigger, but it's not. They're equal on both sides. Right? So sine, cosine, we've established that they're continuous functions, but they're not just any continuous functions. They're continuous functions that kind of oscillate up and down. Okay. So what happens, right? When you actually represent this with Fourier, right? And let's say that you represent with a fair number of terms, you actually get something that kind of looks like the following. Okay, so you have your function here. We have our Fourier series representation, right? And so I'm going to use blue here to represent kind of what a typical Fourier series would look like. Hang on. It's difficult to draw because I drew it lopsided. Sorry about that. Okay. That's probably as good as I can draw. Okay. So whenever you represent something with Fourier, you get kind of this kind of oscillating kind of, back and forth, up and down. Okay. Okay. So that's one thing you can't escape, right? You can make it a little bit better by including more terms before truncation, but you can't get away from that oscillating shape. Okay. So because of this oscillating shape, you can kind of see, right, at the locations of the discontinuity, right, we end up crossing that discontinuity about halfway down between the discontinuity and between the left and right sides, right? Right. So we're going to cross our discontinuity right at that midpoint. So that kind of explains why when we do Fourier, we end up with just halfway in between the two discontinuities. Okay. Okay, and that's just purely just from the nature of just how sines and cosines are. So even though they're continuous functions, we do have to accept their downsides of oscillation. Okay. But we have something else here that's actually very interesting, right? The fact that the function had to travel, or the fact that the sine and cosine had to travel all this way to travel across the discontinuity, right? It's not so easy for sine and cosine to kind of stop on a dime and kind of change direction. Okay. So in particular, right, we kind of have these little, I call them kind of bunny ears that kind of show up, right? So those bunny ears that show up are kind of, we call them kind of overshoots that happen because of the discontinuity. Okay? All right, and that's not a coincidence, and so that is something that you see basically all the time. And so the first person to notice this was some guy named Gibb. Actually don't even know his first name, just know his last name is Gibb. Of course he named it after himself, just like every narcissistic mathematician in history. So this phenomenon of taking a function with the discontinuity, representing with the Fourier, and having these overshoots, we call this the Gibbs phenomenon. Right? And it's a product of the Fourier kind of representation using sine. Okay, good. Any questions so far on the Gibbs phenomenon? Okay. So you might be asking yourself, that sounds very interesting, but wait a minute, right? So that representation that I drew there, it looks like a fairly low level representation, right? Because if you recall from our discussion before spring break, we can alter the accuracy of a Fourier series expansion, right? So remember, we went over this idea of truncation. Right? So remember, truncation is this idea that, in reality, we can't take an infinite summation of Fourier terms, right? We have to cut it off at some point. But the more terms that we include in our Fourier series expansion, the more accurate our representation is going to be, right? And that idea extends to the Fourier integral as well. Okay. Okay. Right. So typically, when we compute Fourier series, right? So I typically only have you compute maybe the first 3 or 5 terms, but technically that summation is supposed to go on to infinity, right? But if you include 5 terms, that's going to be a better representation than 3 terms. If you include 10 terms, it's going to be even better than that, right? But wherever you cut it off, wherever you kind of stop computing coefficients, we call that the truncation. Okay. Right. And so, basically we take our infinite summation, right? And we say that we can't sum to infinity because we don't have an infinite amount of time, right? We're gonna cut this off at some value n, right? Where n is some value less than infinity, but hopefully is good enough. And the higher the value of n, the more accurate your representation is going to be. Right? Okay. So the Fourier integral actually is exactly the same, right? So if you look at our Fourier integral representation, right? So Fourier integral is f of t is equal to integral from 0 to infinity, right? Where you can think of that integral as integrating over all possible frequencies from 0 to infinity. Okay. Now, of course, in reality, you can't do that. So we do have to cut it off, right? So instead of an integral from 0 to infinity, we cut it off at some finite frequency A. Okay? So the term that we give A here is slightly different. And so it's no longer the truncation mode. We call A here the cutoff frequency. And then same logic as with the Fourier series. So higher your cutoff frequency, the more accuracy that you can expect. Okay. Now, what you expect here is that, the higher your cutoff frequency or the higher your mode, the higher your n, right? That should make your representation overall more and more accurate. It should hug your function much more closely without, oscillating. So you would think that the higher that you set your cutoff frequency or the higher you set your n, the Gibbs phenomenon should diminish, right? Right? Because a lot of people see the Gibbs phenomenon as kind of an inaccuracy, right? It's an artifact that, it's not physical. It's not something that's in our original signal and not in our original function, right? It's just an overshoot that's kind of an artifact for Fourier. So as our Fourier gets more and more accurate, you would think that an artifact like that would diminish, right? But turns out it actually doesn't. And that's kind of what makes the Gibbs phenomenon so fascinating. So actually, if you increase the cutoff frequency, it actually makes the Gibbs phenomenon worse.
So if you take away the cutoff frequency, sorry.
So if you increase the cutoff frequency, so let's say that you have a cutoff frequency of, let's say 50 compared to 25, you actually get a worse Gibbs phenomenon at 50 than 25. Even though overall you are getting a more accurate representation, but just that Gibbs phenomenon, that overshoot actually gets worse. I'll show you some pictures in a second. Okay, so I'm going to draw you two images here. So one is going to be with a low cutoff frequency. Another one's going to be with a slightly higher cutoff frequency. Okay, so I'm going to use our same square pulse. Okay, so we have the same square wave. So in black there, I have kind of our same kind of underlying function with a discontinuity. Okay, so let's say on the left here, I'm going to use a non-loud color. Okay, let's say we have some somewhat low cutoff frequency of 8. Okay, now a graph like this, we are going to have Gibbs phenomenon, but with such a low cutoff frequency as well, we're not going to expect a lot of accuracy, right? And so for a function like this, right, we may get something that looks like this. Right? Where with such a low cutoff frequency, the frequency of our sine and cosine is capped at a low level, right? And so we're going to have these oscillations that kind of oscillate slowly. It does jump up at the discontinuity, and we obviously see the Gibbs phenomenon there, but it's actually not as severe, right? Whereas if we come over here, right? So let's say we have a somewhat higher cutoff frequency.
The 1 year is the valley, does it dip underneath?
It does. Yeah, it does dip underneath. So for a higher cutoff frequency for 16, you can see that when you're not around the discontinuity, it's actually going to hug the function a lot better, right? So because our function now can have a lot higher frequency, right? And so we have maybe something like this, right? Where the magnitudes of those oscillations around where the function is stable is much less, but when you get to the discontinuity, the overshoot is going to be even worse. So it actually starts to look something like that, right? So the frequency of the oscillations obviously goes up, and that allows us to kind of hug the function a bit more closely. But around that discontinuity, the bunny ears actually get bigger, right? And this problem is even more exacerbated the higher you make A, your cutoff frequency, right? Right. So in theory, if you were able to set your cutoff frequency to infinity, right, there's something magical that happens at infinity where, the Gibbs phenomenon kind of magically kind of goes away. But it's kind of one of the weird, I call it kind of singularities of kind of Fourier mathematics, where if you keep increasing A, and as long as A stays finite, right, the Gibbs phenomenon that you observe actually gets worse and worse. But something happens, when you do set your cutoff frequency to infinity, where the Gibbs phenomenon just kind of magically kind of goes away. It is a very interesting kind of phenomenon, and honestly, practically is not something that you would observe in practice because you're never going to make an infinite summation of Fourier terms. But it is something to be aware of, as you work with Fourier, especially if you work with kind of choppy, discontinuous signals, to just be aware of that Gibbs phenomenon. Okay, and just know that it just does not go away on its own just by adding more terms to it. Okay. So it's not something you can out muscle, right? It's a problem that's always.
Yes. Just out of curiosity, it seems like, let's say we go to 100 as with A, it seems like the bunny ears will just kind of become a sudden pulse, and they become completely irrelevant.
It's you could argue that, and so that's kind of what people do in practice, where they do kind of increase that cutoff frequency, but then they add a filter where if you have such a huge overshoot, we kind of filter that out. So there's several steps in post-processing that you can do to kind of deal with it. But just by looking at the Fourier series by itself, you can't just out-muscle it by just increasing the cutoff frequency higher and higher. All right, any final questions before we wrap it up for today? Okay, all right, so that's all the time we have for today. So thank you guys for coming. I hope you guys have a good rest of your day, and I will see you guys all on Thursday.
I have way to walk there. I was more curiosity. So what is this? What can this be invested in essentially?
Yeah. So practically speaking, so whenever you're doing any kind of signal processing, you're like processing, let's say an audio signal, there's always going to be some degree of Fourier. You can never just take a raw signal, too much noise, too much interference going on. And so this phenomenon here kind of puts a limit on the amount of Fourier load you can on the amount of Fourier, on the amount of load that you see, right? So the amount of Fourier. So you have to cut it off at some point. And then the temptation is going to be, let's just keep as many frequency. But if you do that, it's more susceptible to things like this. And so there's a balance of let's keep enough loads so that our signal is accurate, but let's not add too many loads, otherwise it gets up. Yeah. And it also kind of gives you some more appreciation for really advanced audio engineering, because because when you're doing, let's say that you're recording a symphony orchestra, you want to maintain as many signals as possible in the frequency, but you want to hold stuff like this. There's a lot of kind of really advanced filtering, a lot of really advanced kind of use to be able to keep all these frequencies, but prevent stuff like this from happening. Because if this was an audio signal, like a spike like that would be kind of like a huge kind of static loud thing that you hear in your headphones, which is not pleasant at all. And so when you have a very nice audio file that has a really nice depth of sound, you can kind of hear everything, but it's very pleasant. There was some pretty crazy.
And does this apply to the radio frequencies?
It does.
Okay.
Yeah. So your radio is kind of doing something similar too, where it's trying to catch some frequencies, but it's trying to damp out things like this.
That's really interesting.
Yeah, it is. It's fascinating. Honestly, beyond what I told you, there's not much more I understand about it outside my own research, but yeah, there's a lot. That's part of why I have a lot of respect. There's a lot of really complex stuff that goes into it, and signals are rarely ever clean, so you're always going to get a dirty signal. So you take something like that and clean it up, and there's something that is nice. It's very good.
Yeah, because my follow-up question was going to be same notes for your radios. Is it just a matter of how high they can get the limit, but then also filter out the static noise versus something that's more of a common radio as well.
Yeah, so for that application, I'm guessing probably their cutoff frequency is much lower because that's real time kind of communication. So you don't really have a lot of time to filter that signal because we want to come up with the time is much more important. And so for that one, I'm guessing they're probably keeping a lower cutoff. That's why, you know, for those ones you hear the noise about those, because there's just no time to apply filters.
I see. Okay. Versus something like Boxer or something. And I say Boxer and probably uses Wi-Fi. But any kind of sensitive radio that can't pass over a mountain, but say 100 feet away with a clear line of sight, it'll be a lot clearer.
Exactly. Yeah.
That's interesting. All right.
Yeah, no, it's really cool. For sure.
I nerded out a little bit over radios. You know, I always got into the nitty gritty with it. And I never